Measurements of temperature are fundamental to recording trends in our climate. Since 1900, the atmosphere has warmed by about 1 degree Celsius, and the zero value on the y-axis, shown on this diagram, is the average of the temperature between 1961 and 1990. As I mentioned earlier, satellites have revolutionized how we visualize the distribution of gases in the atmosphere. The greenhouse gas methane has a number of natural and human sources, but most of these are in the northern hemisphere. As the lifetime of methane is approximately 9 years on average, determined by reaction with the hydroxyl radical, there is not time for methane to be distributed evenly everywhere. Transport from one hemisphere to another is quite slow, as the large circulation patterns in the atmosphere do not cross the equator, and so there is a strong gradient between hemispheres. Note though that the mole fraction does not change that much around the globe, only by about 5%. The hydroxyl radical removes the majority of methane from the atmosphere, and in fact it removes most trace gases, including some toxic molecules like carbon monoxide, which otherwise would build up to dangerous levels. The hydroxyl radical OH owes its reactive nature to an unpaired p electron sitting on the oxygen atom. OH only lives in the atmosphere for around a second, and so is a challenging molecule to measure. At Leeds we have developed several instruments to measure OH. This one is housed in a mobile instrumented laboratory. We have to take the container around to the front of the Parkinson building each time we go on field work, and a lorry then takes it to a port to continue its journey. Inside the container are lasers, pumps, gases, electronics and optics. The instruments are supported by the National Centre for Atmospheric Science, which is based in Leeds. Aircraft measurements have the advantage in that you don't have to wait for the right sort of air to come to you. You can go chasing interesting air masses. The UK is lucky to have a highly instrumented aircraft which enables the composition of the atmosphere to be determined in great detail all around the world. As the OH radical is so reactive, we have had to construct a special inlet which looks a little like a small jet engine to get the OH radical inside the aircraft without too many losses, because we detect it using a laser. FAM stands for Facility for Airborne Atmospheric Measurements. Its home base is at Cranfield in Bedfordshire, close to Milton Keynes. The distribution of ozone around the planet can be monitored from space. Stratospheric ozone, which resides approximately 15 to 50 kilometers above our heads, protects life from harmful UV radiation, whereas tropospheric ozone, which is in the air we breathe, is harmful to humans and plants. It causes more damage to crops than all other air pollutants put together. Ozone is also a very important greenhouse gas. It should be stressed that we don't emit ozone, it is generated purely by chemistry. In the troposphere, this is initiated mainly by reactions of the OH radical, whereas in the stratosphere, this is initiated by the sun breaking the chemical bond between the two oxygens in the oxygen molecule O2. Although satellites are able to measure the vertical distribution of ozone in the atmosphere, usually global maps show the total amount of ozone over a given location on the planet. The amount of ozone in this column is given a special unit, the Dobson unit, and around 300 Dobson units is a normal amount of ozone, with most of it found in the stratosphere. For several months each year, peaking in October, there is a hole in the ozone layer in the stratosphere above Antarctica, as shown in the above diagram. Note that for a given day, in this case October the 23rd, 2011, the satellite doesn't cover the whole Earth. The white stripes show where it missed.